David Smith here with another Flip Classroom math video. A few tips before we start. Remember that you can slow down or speed up the playback if that helps you follow along. You can also pause the video at any point to catch up with your notes or to try the problems before I explain them. Finally, you could turn on the captions and read my words below on the bottom of your screen.
Today's lesson is a review lesson of Chapter 8 from the Oxford University Press for the Applications SL2 course. This is about testing data for validity. Namely, we did three main tests. We did the chi-square test, we did the goodness of fit test, and we did the t-test. So this video is going to review, give you highlights of all that, and we'll finish with doing a few problems. So check this out. Our first test was Spearman's rank coefficient, R sub s. This is best for non-linear data. Now, Pearson's R is calculated in the same way, but there's a difference, and we'll get to that in a minute. But Pearson's R doesn't give you a very good correlation for non-linear data. You could actually have a very strong correlation, it's just not linear, so Pearson's isn't going to show that. So that's why we use Spearman's in those cases. And what we do the same regression as we do for Pearson, but we do it on the data ranks, not on the data. And we had a special process for figuring out those data ranks. You want to make sure you can do that. And then also you want to comment on the strength and direction of the correlation. So the values of R determine that. So that's pretty much what we did with Spearman's rank coefficient. Whoa! Our second test was the chi-square test. And we actually use that test within the goodness of fit test as well. So the understandings that you gain from the chi-square test spill over into goodness of fit. So let's take a look at that. First off, this is not x squared. This is chi-square. It's a chi-square test. Greek letter chi. Okay, so what this test is if there's a difference between what you would expect from some situation versus what is observed, you want to know, is that difference significant or not? So if we flip a coin 20 times and we get 11 heads and 9 tails, does that indicate that that coin is biased or not? It's very possible to get 11 heads and 9 tails, but you want to know, maybe that's an indication of how biased it is. Or let's try it again. Let's try it with 13 heads and 7 tails. Does that indicate bias? So it allows you to compare things like that to say whether or not they're statistically significant. And in our case, the HO, which is the hypothesis that the data differences aren't significant, that means the null hypothesis is true. HO is also called the null hypothesis. So the chi-square could tell you that HO is most likely true, i.e. there is no statistical significance to any differences that you see. Alternatively, HA is the alternate hypothesis. Also shows up as H1, H0 and H1. So you should be ready for that. And what this says is that the difference is significant. It can't be explained by random chance. So that means the alternate hypothesis is true. Now, reaching back to chapter 7, HO indicates that all the data is independent, doesn't matter, doesn't depend on each other. For example, taste in music doesn't depend on whether you're a girl or a boy. It's going to be the same. Whereas in that example, HA would be, if you're a girl, you're more likely to like country western. If you're a boy, you're more likely to like rhythm and blues. I don't know, but that's what HA would be in that music situation. So, the one thing we do, we have a grid. You have to be able to do degrees of freedom. Okay? You have to find your degrees of freedom based on your grid. And remember, it's the number of the number of rows minus 1 times the number of columns minus 1. So you multiply those two numbers here, that gives you your degrees of freedom. And you're going to need to enter that into your chi-square calculation. And so you enter your data into a matrix. And this is a little different than any other chi-square calc we do, different steps on the calculator. So you want to be ready to do that. And then here's where we analyze our results. And this is the same across any chi-square test and all the goodness of fit tests. So once you've mastered it here, it helps you in all the other sections. So if chi-square exceeds the critical value and or p is less than the significance level, then you reject HO and you accept HA. So if this happens, we're saying the differences in expected and observed can't be explained by chance. There's something going on. Girls actually do like country western more than boys. It's not just a random sampling error. Alternatively, if chi-square is less than critical value and the p-value is more than the significance level, then we accept the null and reject the alternate hypothesis. So this would mean that, nope, there's no significant difference. Any little differences you see in observed from expected, that's just going to be based on random chance. Okay. One other thing with this, you're going to need to be able to figure out your expected values. So I'm going to put another one here. We're going to take a look at that in some of the examples, but you'll need to be able to do that to perform this calculation. The third series of calculations we did involved the goodness of fit test, which we also call the GOF test. Let's see right there, that's our abbreviation for that. So you should know that that stands for goodness of fit. So what this test does is it checks your data and compares it to a probability distribution to see whether or not the variations in your data can be explained by chance or if there's something going on. So we compared to 3 different distributions. We had 3 lessons in this section. There's a uniform distribution, which is just the distribution you would expect by chance, often a rectangle. Normal distribution, now you remember that from chapter 7. This is a natural distribution that arises out of a certain set of probability conditions. And then finally there's a binomial distribution, which involved probability calculations involving numbers of trials. So one of the critical things about using the goodness of fit test is you have to know which one to use based on the problem. So if the problem talks about trials, then you know you're in the binomial distribution. If it talks about other stuff, then most likely you're in the normal distribution, or if it's even simpler, it's just the uniform distribution. So you're going to need to know how to articulate normal distribution, which involves a notation, and binomial distribution, which involves those notations as well, and figuring out outcomes and so on. So if the problems are complicated enough, you might need to use your binomial distribution to calculate the probabilities of success so you can find your expected values, because you'll need those to do some of these calculations. Okay, so let's take a look at the hypotheses. HO, null hypothesis, is that the data fits the distribution. And that means that any variations that we see from what we would expect in the distribution, they can explain by chance. So these are just randomly occurring differences that happen naturally, and there's no significance between our data and the distribution we're comparing it to. If it doesn't fit, then the variation can't be explained by chance. And there's something going on, there's something statistically significant that is happening with our data. It can't be explained by chance. So this is why we're doing this test. We think there might be something going on, and so we do the test, and depending on the results we get, we would confirm or not confirm that there's something going on. Okay, now the nice thing is, actually I'm going to, hold on a sec. You do need to calculate your expecteds, I mentioned that in a minute, and your degrees of freedom. It's a little different in these kinds of tests. And then finally, the stat test on the calculator is the same analysis. You do invoke the chi-square goodness of fit test on the 84, that's in the test section, and then but you analyze it the same way. You look at your critical value, your p-value, and you decide whether they pass the thresholds or not, and then you reject HO or accept HO as before. Okay, our last test for validity are t-tests. And this is yet one more way, but it does a different thing. It compares 2 data sets to see if any differences between them are statistically significant. So we can compare data set 1 to data set 2, run this analysis, and it will tell us if they're statistically different or not. So for example, at period 1, I give a test to 28 kids, and I score their scores, and on period 2, I give the test to 23 kids, and I score their scores. And I add up the averages, and it turns out that one period has a slightly high or a higher average by a couple percentage points than the other one. But before I go saying, oh yeah, class period 2 did so much better, I would need to run a t-test to see if that difference is actually statistically significant. Because if it's not, then that little average bump, the little average that's bigger for period 2, really doesn't mean anything. It's just a random thing that happened from that day of that testing. Because I might want to know, oh, if period 2 is actually doing better, then I might want to think about what am I doing there that I'm not doing in period 1. So as a teacher, I might be able to address that situation and bring up my period 1 scores. Okay, so let's take a look. So compares two data sets to see if they're different, uses mean values, and the mean values are mu1 and mu2. So mu1 would be the mean of data set 1, and mu2 would be the mean of data set 2. And like I was saying with that analogy between test scores and periods, the means alone are not enough. You can't use them alone because it depends on the variation of the data, it depends on how much data. There's a lot of variables that depend on whether or not any differences are significant. So that's why we have a t-test. So let's talk about the two hypotheses. HO, null is true. That means that mu1 equals mu2, okay? Any differences aren't significant, which means they are the same. So that would be except HO, so there's no statistically meaningful difference between these two groups, okay? So that's our null hypothesis, and we would accept it. So now there's 3 states where we don't accept and we reject the null, and that is either this one is just that, whoa, these two data sets, they are different enough that that difference is significant. And then, so this is more of a general case. And then these two are a little bit more specific, and that relates to the example problem you're trying to do. This would be for the mu2 to be significantly bigger than mu1. In other words, period 2, their average was higher. That higher is statistically significant. It means that period 2 did better on the test. And this would be the other way. If mu1 was bigger than mu2, it means that the difference there is significant and there's something going on in period 1 that's leading to higher test scores. Okay, so now there's another thing that people find confusing. You're prompted, is this a two-tailed test or a one-tailed test? And that relates to the probability distribution curve. I'm not going to go there. I'm just going to give you a quick and easy down and dirty way to answer that question. So these are two-tailed tests right there. Two-tailed. And the way I get that is that these two tests could go either way. We're not asking, is one of them bigger than the other? We're just saying, is one of them different from the other? We're not trying to figure out if the claim that one is bigger or one is smaller is accurate. We're just saying, are the averages, are the mu's the same? Are these data sets equivalent? We can't explain any little variations other than by chance. So these are two tails, and the way I think about it is they can go either way, okay? So that's like kind of two tails. They can go either way. We're not interested in the direction. Now the one-tailed test would be these guys. These are one-tailed, and T-A-I-L-E-D. How about that? Okay, so they're one-tailed because we're asking about a direction. So this might be, well, I think my period 2 class is better, and I want to prove that. So I'm posing that question at the start of my t-test. So my hypothesis is that they are better, and my HO would be that they're equal. And so this one is one-tailed because I'm really just concerned about that direction. And the similar idea goes with this one. It's one-tailed, but in the other direction because I'm really just concerned about that direction. The reason I'm belaboring this is a subtle point. When you run your t-test, you do need to pick one of these 3 things. And the clue for that is in the question. They're going to ask you a question, and if they say, are these groups statistically different or something to that effect, then you know you're running this or this test. If the question is slanted in any way towards suggesting that one group has means that are bigger or smaller, then you're going to use one of these 2 when you run your calculator, and you're going to do a one-tailed test. Okay, let's do a chi-squared test problem. It's going to walk us through all the steps you need for a chi-squared calculation. So here's our scenario. We have 5 movie genres, thrillers, romance, history, horror, and comedy. And then we have males and females. And we're trying to figure out, is there a clear difference in taste preferences between males and females? And so we have all this data, and I have to say, it's a little hard to data snoop something like this. It's really hard to check and see if the differences are significant. If you stare at it long enough, you might be able to come to some conclusion, but my guess is you're not going to feel real good about that. So data snooping is really not going to help us here. Plus, no matter whether it does or not, you got to do your calculations. So, is movie preference independent of gender? So that would mean the HO is yes. We have accepted the null. The HA would be no, it's not independent of gender, in which case we reject the null. So there's our language and our notation around that. First prompt, find the degrees of freedom. Now when you have a matrix like this, degrees of freedom are they're columns minus 1, 1, 2, 3, 4, 5. It's columns minus 1 and rows minus 1. So we just have 2 rows, so that's 2 minus 1. So that ends up being 4. So our degrees of freedom for this scenario are 4. Now, we're going to need to calculate expecteds for all of these. Okay, I'm going to show you how to do one, and then if you feel like riding along and actually doing this calculation, you'll need to do that step for all of those. And then when you're finished, you want to check and make sure that the totals are the same. Okay, so if we want to find out the expected number of females that like horror, this would be the number of females if there was no statistical difference between males and females with respect to liking horror. Then here's what you do, is you multiply the total of the row times the total of the column, and then you divide by the total. So the total of the row for females is 93. The total of the column for horror is 50. 93 times 50. And then, of course, our total, we have 266 people in this whole survey. That's there. And when we do that math, I get 17.5. Now, as a side point, keep your decimals in your expecteds. We do know that you don't have 17.5 people ever, but this is for calculation purposes, not for actual, like talking about reality purposes. Okay. So if you're feeling like you want to run this calculation yourself, you're going to have to pause the video and find your expected values for all of these 10 values in the table. So maybe you've put this table into your notes and you've left enough room to put them next to it. Maybe you need to make another table to do that, but you'll need to do that. Otherwise, just come along with me and we'll finish this calculation up. Okay, so you've put the chi-square calculation into the calculator, and what comes out is 11.1. You also need your p-value, and what comes out there is, so now we have our chi-square and our p-value. So now you need to have a critical value and a significance level before you can go further. Now, in reality, people who do this kind of work, they look these things up in a table, but the IB is not teaching you that part of it. They're just giving you the values that you need for each calculation. So for this calculation, the critical value is 9.49 and the significance level is 5%. So now compare these 4 numbers and decide whether to accept or reject the HO, and be able to say why, provide the reasons why, the mathematical reasons based on your analysis. Okay, it's clear that we reject the HO, the null hypothesis, meaning there is a significant difference between men and women and taste in genres of movies because our chi-square is greater than the critical value. It exceeded the critical value, so oops, no HO. Similarly, the significance level is less, the p-value is less than the significance level. So you have to rise beyond significance to accept the HO. So both of these numbers confirm that we reject the HO. Now, one word of advice. If you do a problem and you get conflicting results, then one of 2 things is most likely happened. One is that you've forgotten which way these things go and you're comparing them both greater than or both less than, which is a mistake. You want to figure out which one has to be greater and which one has to be left. The second one is that you've made a mistake somewhere in your calculation. Something got entered wrong, something didn't work quite right, because they really should move in the same direction. You're not going to get a data set that shows a strong reject based on critical value, that shows a decent accept based on significance level. It just doesn't work that way. Let's do a t-test. But before we start, I want to point out that this problem could contain no hints that it's a t-test. And you have to recognize that we're comparing two different data sets to see if they are statistically different or not. Okay, so you'd have to recognize that. Here I'm giving you the prompt. So here's our scenario. We got First Academy and we got Old Town School. These are two IB schools, and the IB coordinator at First Academy thinks her school results on the full IB program are better than Old Town School. So she thinks our school is better and all that stuff. So she gathers up some scores. She gets some scores. I'm not sure where she gets them from, but she gets a bunch of scores. So here's her Academy scores and here's her Old Town scores. So HO, null hypothesis, is that mu1 equals mu2, and the alternate hypothesis, because she thinks her school is better, is that mu1 is greater than mu2. So we can't calculate the averages, just compare those. We have to run a t-test to see if those differences in the averages are significant or not. Question for you, one or two tail? Pause the video, think about that for a minute. Okay, if you came up with one tail, you're right. We're only interested in whether or not mu1 is bigger. So in a way, you could say the tail is going that way. The question isn't asked, are they different? Because if we asked it that way, then it's a two-tailed test. But in this case, it's a one-tailed test. Okay, so that's going to influence what you select on your calculator when you do your t-test. Okay, go ahead and do your t-test. Put in your data. There's really not a whole lot of other things for me to say. Do your t-test and come on back with your t-value and your p-value. Okay, for my t-value, you get minus 0.706. For the p-value, you get 0.244. Okay, at a significance level of 0.05 or 5%, do you accept or reject HO, the null hypothesis? And think about that and write a reason for why you have the answer that you do. When the p-value exceeds the significance level, we accept HO. The null hypothesis is true. There's no statistical difference between the IB scores of these two schools. So P greater than SL, accept HO. All right, let's do a calculation with Spearman's correlation coefficient, his ranked correlation coefficient. So remember, this calculation does not use the data, it uses the data's ranks. Okay, context. Is reaction time correlated with age? So we have some data. Now these are data points. This is a 32-year-old with a 0.35 reaction time, and so on all the way down. Now we're doing Spearman's. Presumably we did a Pearson's, and we didn't get a very good correlation. But then we thought, wait a minute, maybe this isn't linear. Let's check with a Spearman's ranked correlation and see, maybe we'll get a good correlation there, and we know it's a non-linear correlation, but a correlation nonetheless. So our hypothesis is, got that backwards. HO is no, there's no correlation, and HA is yes. Okay, a little bit of a switch there. Glad you caught that. Okay, so HO, no correlation. HA, there is a correlation. All right, so the next step is to rank the data, and I like to do it right on the same table in the same spot. I know our book prompts us to make a data rank table, but I think there's room for confusion there if you have two tables. I just like making another row right next to my data with my ranks. So go ahead and pause the video, rank that data, and come on back. Okay, I added my ranks on there, and in this case we're ranking from quickest reaction time to slowest reaction time. But the ranks are working like on age, that's the youngest, not the oldest person. It doesn't matter which direction you create your ranks, create it in the same direction on both of your data points. So don't go like smallest to biggest on one and then biggest to smallest on the other. You need to do it in the same way. So this is the lowest age, that's got the first rank, and this is the shortest reaction time, that's also got the first rank. Another thing to remember, notice how we have two that are the same reaction time, a 20th of a second. These would normally occupy positions 2 and 3, but they're the same. So we want to weight them in the same way. So we give them the average of the positions they would otherwise occupy. So this gets a 2.5 because that's the average between 2 and 30, and so does this one. Now that uses up both the 2 and the 3 rank. So you're going to have a 1, 2 2.5s, and then a 4. Don't go to 3 next because you use that with the 2 2.5s. Okay, so now all you got to do is do the same calculation you do with Pearson's, but instead of putting in your data, you go ahead and put in your ranks. Now, a pro tip, if you really want to be thorough, put in 4 lists and just put in these two in L1 and L2, and then put your ranks in L3 and L4. Or if you're doing it on the Inspire, just make 4 columns, label them in a way that you can identify them later. So if you're not sure, you got a problem that's open-ended, I might just put all my data in there, and then I can just run my regressions on the data, and then I can run my regressions on the ranks and see which gives me a better correlation, see what's going on there. Okay, so now that you've ranked the data, I want you to pause the video and go ahead and do the Pearson's linear regression. These steps are the same. You're just using it on the ranks. Go ahead and do that. Come right back. Okay, I did the calculations. I get my R sub S. Remember, the sub S is Spearman's calculation. I get a 0.775. Now remember, 0.75 and up is strong correlation. So we have a strong, and it's positive, and it's positive. Now, what that means is, as age increases, so does reaction time. And strong positive. So it's pretty well proven by our data calculation. You can also see that by data snooping. If you just look at this, you're going to see that the higher the age, the higher the reaction time. It's right in the data. But Spearman's confirms that it's a strong correlation. One last example. So we have a die, 6-sided die, numbered 1 through 6, and we roll it 90 times, and we record the frequency of each outcome. So 1, 2, 3, 4, 5, 6, and this is how many we got of each. Now, our hypothesis, our HO, is that it's a fair die. Our HA is that it's not fair. For example, maybe somebody was playing a dice game with somebody else, and that other person just kept winning, and so the person that was losing was going, is this real or are these rigged? So he got one of the die, he rolled it 90 times, this is what he got, and now you're going to help him analyze his data to see if you think it's fair or not fair. Now, if you data snoop this, it looks kind of like it's fair. These numbers aren't varying too much. They're pretty close to each other, which is kind of what you expect because each outcome on a die is equally likely. Okay, so there we go. So what we need to do first is find the probability for each one. So what is the probability of each outcome? And that's easy. That's 1/6 because they're each equally likely. So the probability of each outcome is 1/6. So you might get problems where the probability of each outcome is different. They might tell you the probability, or you might even need to figure it out. Like maybe he's tracking whether it's even or prime, or both. Any number of different things. So you might have to put on your thinking cap to figure out your probabilities. In this case, it's pretty straightforward. Now we need our expected values. So let's just say this is the probability, and this is the expected. So I'm going to put that right along here. Like I said before, I'm a fan of keeping everything in one place so I can look at it nice and easily. So your expected is just the probability of the outcome you want times the total trials. So we roll this die 90 times, so we would expect 1/6 of 90 for each of these for our expecteds. So let's do that. I don't know why I needed to walk away from that, because 90 divided by 6 is 15. I can do that in my head, but that's what I did. And then I also kind of made this table a little bit more clear. So 1/6 times 90 is 15 for all of these. So the expected values are 15 for each of them. And this is where data snooping is really suggesting that this is a fair die, that HO is true, because our observes are really close to our expecteds across the board, and there's no what would seem like an outlier, like maybe 4s, we got 22 of those. That would make me worry, but everything is really close to the expecteds. So when we do our analysis, I'm going to be expecting that I can reject HO. Okay, so the next step is to find the degrees of freedom. So go ahead and pause the video and do that. So for the goodness of fit calculation, the degrees of freedom is just the number of categories minus 1. So we have 6 categories. Those are 6 different outcomes on a 6-sided die. We subtract 1, so our degrees of freedom is 5. So now you have everything that you need to go ahead and enter into your technology, Desmos, TI Inspire, TI-84, or whatever else you use, and go ahead and put that in there and run your goodness of fit calculation. It's a chi-square calculation, really. It's just we're doing it in a different context. And go ahead and get your results, get your chi-square, get your p-value, and come back. Okay, here's what I get. I get a chi-square of 10, and I get a p-value of 0.1247. So the problem gives us a critical value of 15.086 and a significance level of 1%. So now evaluate that and tell me whether you can accept or reject HO. Okay, chi-square is less than critical value. We haven't exceeded it, so we can't reject HO. Okay, here's what I get. Chi-square 10, p-value of 0.1247. Okay, so now we have to analyze that. The problem is going to give us a critical value of 15.086, and it gives us a significant level of 1%. So now pause the video, analyze these numbers, and tell me whether you can accept or reject HO. Accept HO. The critical value, the chi-square does not exceed the critical value, so we can accept HO. Similarly, the p-value is greater than the significance level, so again, that says accept HO. One last thing. What are we comparing this distribution to? Because you'll recall, goodness of fit tests compare data to uniform, normal, and binomial distribution. So pause the video and think about that for a sec. This test is testing whether or not the data fits a uniform distribution. So HO is it does fit, HA is it doesn't fit. And just to remind you what a uniform distribution looks like, that's when you have all these equally likely outcomes, you're going to get roughly a rectangle. This is not quite a rectangle because we had some variation, but the uniform distribution is this rectangle right there. 15 of each outcome, it makes a rectangle. So that would be a uniform distribution in this case. So I hope you enjoyed this video. I hope it helps you. I hope it helps you feel ready for the unit test if you're in my class. If you're in another class, I hope it covered the points that you needed help with, and good luck with your math.
Now that you've finished, write down any questions so you can bring them to our next class and get some help. Remember that you can always watch the video again to improve your understanding. If you enjoyed it, please click the like button down below, and if you'd like to help me grow my YouTube channel, please click subscribe.